Chapter 4, Chemical Reactions. Okay? Three major classes of chemical reactions. They deal with precipitation, acid-base, and redox. Okay, so water is a very cool molecule. It's what we call polar, which means it has an uneven electron distribution, which means when the hydrogen, oxygen, and water get together, the oxygen likes the electrons more. So it pulls the electron farther away from the hydrogen, making it uneven. Water also has, or oxygen also has, a couple of lone pairs on the top that aren't part of the bonds. That's why they're called lone pairs. It causes the molecule to be bent. The water is both bent and has an uneven electron distribution, which means an uneven electron distribution. It has a positive side and a negative side, or ready, a polar bond. The water dissolves things that are very similar to it. The phrase is, like dissolves like. Water dissolves things that are similar to water. Water is polar, so it dissolves polar substances. Water is small, so it dissolves small substances. It does it very well. In addition to dissolving things similar to it, it also dissolves things like ionic compounds, which are made up of positive and negative ions. Since water is so polar, it has a positive and negative end. They interact very strongly with things that have positive and negative parts, like ionic compounds. And here we have H2, which is symmetrical. In A and B, we have water. We show it with electron distribution. We can see where in some parts where the electrons are more, it's negative, and where they're less, it's positive. So the two lobes on the bottom are the hydrogen, so they lose the electron most of the time. Not all the time, it's still part of the bond. And the top is the oxygen, which likes the electrons more, so it pulls it tighter in. Okay? Water has polar bonds, which is an unequal distribution of electrons. The oxygen likes it more, so the arrows point at the more negative one. Okay? And it's bent, so it makes the whole molecule polar. So it has polar bonds, and it's a polar molecule because of its structure. The lone pairs on the oxygen force the molecule to be bent. Here we have water dissolving ionic compounds, which it does really well in creating aqueous solutions. It does this because water's positive part is attracted to the ionic compound's negative part, and the positive part of the ionic compound is attracted to the negative part of water. The issue you're going to have is some molecules won't dissolve because their charges are too large. So if you have a +2 or a +3 or a -2 and a -3, they don't dissolve that well because they stick together very well. In this scenario here, the positive negative ones are more attracted to water than they are to each other, so they dissolve. If they were more attracted to each other, they wouldn't dissolve. And here we have three different substances. The first one is a pure substance of water. It doesn't conduct electric current. The second one's a pure substance of ionic compound. Now, it would if it had freedom of movement, but it doesn't, right? And water won't because it doesn't have positive and negative ions. But when you put the two together, you end up with a whole bunch of positive and negative parts inside of it and freedom of movement, which is what we call an aqueous solution. These are called electrolytes. Okay, we will do 4.1 later. 4.2, okay, concentrations and solutions. The main one is molarity. Okay, molarity is moles over liters. And concentration basically means I've crammed a certain amount of material in a certain volume of a solution. Okay, so the more I put in there, so if I have salt water and I dump 1 teaspoon in 1 liter of water, that's concentrated. I dump more in there, it becomes more and more concentrated. Okay? The solvent is the part that's dissolving, and the solute is the part being dissolved. In most reactions, they need the stuff to be in solution, especially ionic compounds. It needs to be dissolved in water to react to give it freedom of movement so it can collide. Molarity is moles over liters, and it's also a conversion factor. Simple diagrams start with grams, go into mole, then go into molarity if we want the volume, which is on this side, or we can go into the amount of substances, which I don't know why you would. Avogadro's number to figure how many things are actually in there. 4.4, 4.5. You know, this is a simple kind of demo. This is what we call a volumetric flask. And we typically use these when we make solutions. I do. Okay. And so what I do is I fill it up with a little bit of water. Right. I dump all of the actual solute I want to dissolve inside of it in here. So I'm trying to get to a certain molarity concentration. I measure out the mass of the stuff beforehand, convert it to mole in the calculator, and then I'm going to divide by. In this case, this should be 1 liter because it's easier. I like to divide by 1. And so if you look here at the very last screen and see, you can see how much water I fill it up to. And that is exactly 1 liter. That's why it's called the volumetric flask. And this is just a separation between the difference between concentration and dilute. Concentrated means I have a whole bunch inside of it. Dilute means I have not much. And you can see, according to these things, the color changes depending on how concentrated it is. The solute makes it turn a certain color, and the more the solute you have in there dissolved, the darker the actual solution becomes. Coming back to all those. And so this is what we call, there's actually 3 different types of reactions going on here. The first one is a molecular equation. Up until this point in time in your chemistry lifetime, this is the one you normally do. You assume everything's behaving like a molecule. The problem is silver nitrate and sodium chromate are not molecules. Okay? In the second step, we show them as if they're broken apart. So when we look at the mid part here, which says atomic level, we can see that silver nitrate really looks like this. Not together. Once you put it in water, it dissolves, so it breaks into its ions. And sodium chromate does the same thing. It breaks into its ions. And then when you put them together, you end up with the chromate and the silver bonding or being attracted to each other. Bonding is probably a strong word. Being more attracted to each other than they are to water, so they stick together. And the sodium and the nitrate don't do anything, so they stay in solution because they're still more attracted to water than they are to each other. They have a small charge. So then we show the total ionic, which means we break everything apart but this thing. That says little s next to it. If it doesn't break apart in water, we call it a precipitate. So silver chromate is the precipitate in this reaction. These other ones didn't do anything. The Na and the NO3 didn't do anything. So they're what we call spectator ions, like spectators at a sporting event. They think they're part of the game, but they're really not. It's the same kind of thing here. The Na and the NO3 don't react with anything, so they're not included in the overall or the net ionic. What really happened? And what really happened during the course of this chemical reaction was I formed a precipitate. Here up in the mid-level, you can see it's the red and the gray ones. So the total ionic just shows you how they're breaking everything apart. I just call it ionic. I've never called it total before. So you break everything into their parts, like they did the silver and the nitrate. Okay, and then spectator ions are things that appear exactly the same on both sides. We essentially eliminate them when we go to the net. They don't need to be there because they're not really reacting. And here are 3 types of equations. Molecular, which we use to balance it. Ionic or total ionic shows you how everything's broken apart in water, what it really looks like. And the net ionic eliminates the spectator ions and shows you what's really happening. Okay, so these are precipitation reactions. We basically take 2 soluble substances dissolved in water, aqueous, mix them together and form a precipitate. Insoluble. So insoluble and soluble we call relative terms, which means some things are really soluble, some things are not so soluble, some things aren't soluble at all. It's all relative to each other. It's a comparison between the two. And it's possible to have more than one precipitate form, but you really don't get it most of the time. And here we have another set. All right, the top line is the molecular. If everything behaved like a molecule, which we know the Na and the F separate in water, and the C and the Cl separate in water. And then the bottom one, right, should be the net ionic. We've eliminated the spectators from the total ionic to the net ionic. How do you know whether precipitate forms? We have something called solubility rules. Insoluble means it does form a precipitate. It's a solid. Soluble means it does dissolve really well. And you're always looking to see how positive and negative ions interact with each other. So these are some general solubility rules. You can see that all common compounds from group 1A, it doesn't matter what we call them, group 1 elements, they never form compounds. Okay? Ammonium never forms a compound. Nitrates never form compounds. Okay? So they're what we call soluble. They don't have any insoluble parts. And then some of them dissolve well in water, some negative ions, but some of the ions don't let them dissolve that well in water. And it's really about something called Coulomb's law. Coulomb's law basically tells us that the larger the charge, the better they sit together. The smaller the atom, the better they sit together. So things like lithium and sodium are small and with a small charge. So those ones dissolve relatively easily because of their small charges. So this is a pretty common precipitate, the sodium iodide. Okay? It's a double replacement reaction. We'll talk about those as we go. So they've separated. They showed you all the stuff going on. They went ahead and they took the top line is the total ionic. The next line is the top line is the molecular. The next line is total ionic, and your bottom one is your net ionic. You've removed the spectator ions. So from each step, what we've done is the top line in the molecular, we just wrote them. In the total ionic, I separated anything aqueous into its ions based on solubility. And then the last line, I write the net ionic, which basically means I eliminate the spectator ions. These are called double displacement or double replacement or metathesis. You exchange the negative ions. They didn't do it that way, though, but I will. Look at all this good stuff. I don't want that on there. I gotta eliminate that for you. Okay, so this is just another roundabout how to go between one substance to another. Okay, using moles. So we can go in volume, we can do mole ratios. There's all kinds of good stuff with this. We will do this as well. Lots of problems here. Okay, the second type of reaction. First one is precipitation. Second one's an acid base. And essentially with an acid, you have hydrogen, which is a proton, and you're going to go ahead and produce it. So there's two different definitions. They're going to use what they call the Arrhenius definition. That's what this is. It's a simple one. When you put an acid in water, it produces H positive or H3O plus. It's called hydronium. And when you put a base in water, it produces OH minus. M stands for metal. So they're dealing with a pretty strong base and a relatively strong acid. When you mix the two together, you get a neutralization reaction. And on the pH scale, one substance is neutral. It's called water. So essentially what you're doing is you're adding the H positive that you produce from the acid to the OH minus that you produce from the base, and you put two H's together and one O together, and that gives you H2O. So the hydronium ion is H3O plus. It's pretty strong and attracted to water, which means it dissolves well in water. Here's a table of strong and weak acids and bases. You only need to know the strong. There's a lot more weak than there are strong. So the strong ones are on top. There's actually 7 of them, depending on the textbook. There's a 7th one would be chloric acid, and it's HClO3. Okay, so you need to know the 7 strong. And then the bases, strong ones, those are them right there. You notice group 1 breaks apart well in water because they're +1 charges, so that means they break apart well. There's lots of them. Ammonia is one you need to remember as a weak base. Okay. Acid and base are electrolytes. The stronger they go ahead and break apart in water, the stronger the electrolyte and the stronger the acid. They don't break apart well in water, but they break apart a little bit. We call them a weak electrolyte or a weak acid. Now this is another definition of acid-base called the Bronsted-Lowry. And what it is basically you have a proton transfer. And a proton is an H positive ion. So you're just switching the protons back and forth between two things. So the acid is a proton donor, and the base is a proton acceptor. Now, in some scenarios at acid base, one that you're pretty familiar with, you have an acid you mix with a base and it produces carbon dioxide and water, right? So carbon dioxide as well as the water. And so in this example here, the NaHCO3 is what we call baking soda. And the CH3COH is called vinegar. You might have done this reaction as kid volcanoes. And you mix them together, the two, and you should get water as a product, because that's called the neutralization reaction. Acid plus base yields salt and water. But you also get H2O here. And technically, what you get here is not what they're showing. We'll have to show you when I get there. This should be H2CO3. Okay, now, in the molecular, they have everything together, like they should. The total ionic, they've separated the NaHCO3. They didn't separate the CH3COOH because it is a weak acid. Okay, it's a weak acid. So because it's weak, they're not going to separate it, because weak acids don't dissolve that well in water. They don't produce ions, They don't break apart into ions well in water. Okay, and then we go to this side. We have this base broken apart, and we have CO2 and H2O. So the only thing we're eliminating from the total ionic to the net ionic in this reaction is the Na positive. It's because this acid doesn't break apart that well. Okay, titration is a nice, simple reaction. We go ahead and we know the concentration of one substance, and then we go ahead and add a substance we don't know the concentration of. And it's going to be acid and base. That's usually the way they are. They don't have to be, usually the way they are, but the one we explain it does. And the concept's based on the neutralization. What we're going to reach is something called the equivalence point. The equivalence point is when the acid and the base are totally canceled out. So all the H plus from the acid, all the OH minus from the base are reacted totally. There is no limiting reactant at the equivalence point. There is no excess. The end point is based on what we call the acid-base indicator. The acid-base indicator changes depending on the equivalence point of the end point. So if I have an equivalence point of 7, then I want to choose an acid-base indicator that changes around 7. So the end point is where it actually changes. So I want to match up the equivalence point to the end point. So I would need a table or some kind of information to let me know where certain indicators change color. Whoops. Now, this is a typical classic acid-base titration, which you didn't get to do if you're juniors in high school, which is terrible, but it's one we all do. And in the scenario, we use the indicator called PTP, phenolphthalein, and phenolphthalein turns pink in a base, right around 7. So we take an acid and a base. So in the beginning one, we just have acid, and we're going to add base to it, the OH minus. We put the indicator in there with it, and we go ahead and add the actual base until it changes into a light pink. At that point, that's called the endpoint, where it slightly changes. That's where the indicator changes. And if we choose a good endpoint close enough to the equivalence point, then that means we're going to be able to come to the equivalence point by the color of the indicator. Awesome. All right, this is our third type of reaction. It's called the redox reaction. And the redox reaction is an exchange of electrons. It's an exchange of electrons. Oxidation is a loss of electrons. Reduction is the gain of electrons. Okay, so the saying is, Leo goes grr. Leo the lion goes grr. Loss of electrons, oxidation. Gain of electrons, reduction. I had to think for a second. Okay? And together, they have to happen together. One has to lose an electron for another one to gain an electron. So these go hand in hand, so we call them redox. And now oxidation should become more positive over the course of the reaction, whatever you're talking with, and then reduction should be becoming less positive. That's how I like to describe it as far as positivity. Right? Now, a reducing agent is something that's oxidized, because using the reagent makes it seem like you're causing something to be reduced. And so in order for something to be reduced, it has to have electrons. because it wants to gain them. So whatever's being oxidized is causing the other one to be reduced. And by the same token, it may be easier to see, in order for something to be reduced, it has to gain electrons. Well, it has to gain them from somewhere, something that's losing them. So it's called the oxidizing agent. Okay, and here we have in the top one, the magnesium is losing 2 electrons to the oxygen. So the magnesium is becoming more positive. You can see it goes from 0 to +2. Right? And so that means that it's losing electrons. And the oxygen is going from 0 to -2. Therefore, it's gaining electrons. So the magnesium is being oxidized, and the oxygen is being reduced. Okay, and this is just a ionic compound, and the bottom one is a molecular compound. They call it covalent, but covalent type of bond. And here we have H2, which elements are 0 charges, and Cl2, 0. And when they come over here, the H ends up being slightly positive because it's losing the electron, and the Cl ends up slightly negative. So what we've done is we've taken the H and we've gone from 0 to positive, so therefore it's being oxidized. And the Cl goes from 0 to -2, so therefore it's being reduced. And here are some general rules. I'll give you a copy of these as well, maybe more extensive. Number 1, and if it's in its elemental form, it's an element, not part of a compound. It has a 0 oxidation number. Number 2, if it's a monatomic ion like chlorine or sodium, it's usually their ion charge. Right? It'll be written right there on the sheet for you. 3, we want to go ahead and take all of them and add them up to go ahead and get the overall charge, because atoms are 0. So we would want everything to cancel as we go forward. Okay, and then other rules are underneath. Hydrogen's a +1, oxygen's a -2, right? Group 1 elements are +1, group elements are +2. And this is another show of everything on here. X is being oxidized, so it's losing electrons, so therefore it's the reducing agent, right? And it increases its oxidation number. It becomes more positive, right? And Y is gaining electrons, so it's reduced, therefore the oxidizing agent, and it's becoming less positive. Okay. The redox are a little tricky how to balance, because it's based on a couple things. Most of it is how much are they actually changing by, right? And so in these cases, we're exchanging electrons, so the electrons would have to be balanced in an oxidation or a redox reaction. Okay, so the first thing you do is you assign all the oxidation numbers to the atoms. Use your talents you've learned on the last slide to go ahead and do that. Then you have to tell me which one's being oxidized, which is being reduced. We're not going to have 2 being oxidized and 2 being reduced. One will be oxidized, one will be reduced. We'll go from there, right? Then we get to figure out how much electrons are being lost and gained, okay? And after that, we have to go ahead and make sure those are balanced. So balancing redox reactions is all based on making sure the electrons lost equals the electrons gained. That's where they have to be. In this example on the bottom, you see manganese is +7 on the reactant side and +2 on the product side. So therefore, it is being reduced. It is gaining 5 electrons. And then the carbon, right, is +3 on the reactant side and becomes a +4 on the product side. The problem is there's 2 carbons there that are doing it. So there's actually 2 +3s going to 2 +4s. So there are 2 electrons being gained on that one. All right. So these are four of the 5 reaction types. All of these are redox. We know they're redox because they have elements in them. So in the combination reaction, you're putting things together. You have X plus Y, right? X plus Y. So those are 2 elements, and they're coming together to form a compound. So the compound has to have charges on it. The individual parts of a compound have charges, but the elements are all zeros. In a decomp, it's just the opposite. And actually, decomposition is the opposite of combination. Okay, sometimes we call it composition or synthesis in the first one. Decomp, you're breaking it apart, so you're breaking it into its elements. Now, decomps and combinations are not always redox. They can be if they come from their elements, but not always. Single replacement are always going to be redox, always, because you always have an element going into a compound. Okay, and this is spelled displacement wrong. This one never is. I don't know why that's on there. But these are actually 5 reaction types. They're all here. These are the 2 displacement ones. Combustion is always going to be redox because you have oxygen on one side all by itself, which makes it have a 0 oxidation number. Okay, and here what we're doing is taking 2 elements, potassium and chlorine, both have 0 charges. This is a combination reaction, becoming part of a compound, and now they have charges. This is the decomp. We have the compound breaking into its elements, which both have 0. A single replacement. This one's an element going into the compound, so it's 0 with +1. And let's see, this is just a normal reaction. We have H2, which is 0. You're reacting with nickel. So in this one, you have the nickel is the element to start with because it's a solid metal. And it goes into solution, so it becomes +2. And the H is a +1. This is part of the acid, and it goes to 0. And this is a single replacement reaction here too as well. Silver is going ahead and changing as we're going from a compound into an element, so it's changing its oxidation numbers. This is called an activity series. This is strictly for single replacement reactions. And what it means is the ones on top like to be oxidized. So lithium and potassium, you never find on the surface of the Earth is just the elemental forms of those things. They like to be part of compounds. They're what we call losers. So lithium and potassium are the biggest losers on the activity series. On the other hand, silver and gold, when you find them in nature, they tend to be in their elemental form. They don't like to be part of compounds. So they reduce better than oxidize. The lithium, right, is a better metal than gold. We think of it as losers. So elements that are on the top are more likely to oxidize than elements on the bottom. We write them together in single replacement reactions. We can determine if a reaction will occur based on this chart.